Okay, so the plan today is to kind of wrap up our discussion about confidence intervals and then talk about hypothesis tests again. So we'll kind of see hypothesis tests from a more kind of classical way using the central limit theorem as opposed to doing the simulations that we did earlier in the semester. So I just wanted to pass along this info. The university asked me to share this with our classes. So you hopefully have been getting emails about the various vaccination clinics that are going on campus as well as around the city. But yeah, everyone's eligible. You're allowed to bring a family member. So I know that some students have gone to the one on campus and said it was super easy. So last time we were doing confidence intervals for a proportion, and I just want to kind of be sure that we did this in a couple of different ways. So we were doing a confidence interval for what proportion of people in the US, now that we had the vaccine slide up to begin with, seems appropriate that we're talking about vaccines, like what proportion of the people in the US at this point are not planning to get vaccinated. And so there was a study that was done, 1,082 people. Out of that sample, 29%, 413 said they weren't going to plan to get vaccinated. So we constructed what was called the walled confidence interval, which is kind of the equivalent of what we did for the mean, where we take our initial point estimate and then we build in a margin of error that depends on the standard error and the confidence levels. That's what each of these terms are referring to. Then we talked about a modified version of that called the Agresti-Cole confidence interval, where we included 4 extra observations and we assumed that 2 of them were successes, and that gives us a slightly different type of confidence interval. And so you can kind of compare, we did these last time, you can kind of compare that, okay, they're like not drastically different, they're pretty similar estimates, but there are different ways of doing it. And then we also talked about the score estimate. And I didn't get in and solve this, and I'm not going to solve this over Zoom, but just to kind of motivate where these like really horrible looking formulas come from the score confidence interval is we kind of use this idea over here. So this is like, that's a formula for a z-score, right? It's almost like p minus p hat over the standard error. So we're trying to find what is the value of p that's going to give me a z-score that's going to be 1.96 standard errors above the mean. So we pick a sample, we calculated sample proportion p hat, and we're going to solve an algebraic equation to figure out what is the p value that's going to give us a z-score of 1.96. And I kind of skipped some of it, but it's solving a quadratic formula. When you solve this quadratic formula, we get these formulas over here. So basically, this is telling us, okay, if you solve for that equation above, we would have found this formula. And if we set up a similar equation and set it equal to minus 1.96, that would give us the lower cutoff. So these are what are called the score confidence intervals. And we could plug all of these values into the formulas. They're horrible looking, as you can see. And the nice thing is with R, it has a built-in formula that will do that for us. So that's what the prop test does. So it's important to know, like, there are all sorts of different types of confidence intervals that we can do for a proportion, the wall, the Agresti-Cole, the scored confidence interval. This formula gives us the score confidence interval. So if I plug the number of successes and the sample size in, set the confidence interval equal to 95%. This is what the score confidence interval is, and we can compare it to the other two. And you can see, they're all pretty much the same sort of estimate. So on your homework assignment for tomorrow, you have to do a confidence interval for proportion in these different ways and kind of compare them. So are there any questions about that? I think that's pretty much where we left things last time.
Real quick on that homework question you're talking about.
Yeah.
It asks us to do the prop test and the score confidence. So do you want us to actually input that long formula?
So yeah, so that formula I did enter into the R markdown file that we used last time. So we'll get into that in a second. So I can kind of just show you, like, I did try and enter the formula in for you, so you can use my work if you want and use that formula. Okay. Yeah. Yeah, so that's a good question. When I open up the R markdown, we can talk about that. Yeah. Okay. So the last thing I want to talk about on this worksheet before we get back into hypothesis testing is how we can do confidence intervals for a difference in two proportions. And it looks kind of similar to the standard error that we use for difference in two means. That one had like sigma over n. Here we can approximate the standard error. Can be approximated using this formula up top. So otherwise, I don't want you to look at this formula and think that this is an entirely different process for finding a confidence interval. It's usually the same. We take the statistic from the sample that we observe, and then we go minus z alpha over 2 times the standard error. Move that down so it's easier to read. So one thing that these confidence intervals all have in common, again, they all look like they have slightly different formulas, but the general idea is the same. That is, we have some parameter that we want to estimate. We don't know what it is. So we start by collecting a sample, and we use the statistic from the sample as our point estimate. And then we build in a margin of error that depend on our confidence level and the standard error. And the thing that changes in each of these problems is based on the parameter that we're working with. The sampling distribution has a different formula for the standard error, but otherwise it would be the same. So we could calculate this using a walled confidence interval up here, or we can calculate it using a scored confidence interval using the prop test. So just keep an eye out for what method you're told to do. So the idea here is we want to come up with an estimate in this case for is there a difference in the proportion of Democrats that said they're not going to get vaccinated compared to Republicans? Is there a party slant that's playing a role in this? So from that survey, 368 Democrats responded to that survey. 40 of them said they weren't going to get vaccinated, and 292 Republicans responded, and 120 of them said that they were not going to get vaccinated. And our sample sizes, right, are different. There's no reason why they would need to be the same. We don't have matched pairs or anything like that here. These are two independent samples. There's no way to match a Republican with a Democrat in a natural way. So if we were kind of using the walled confidence interval, then we would calculate these things by hand. So I would say, I'll say P1 is a Democrat and P2 is the Republican. So I would take my 40 out of 368 minus the 120 out of 292. And let me just do some calculation in R. So that comes out to so that first proportion is about 11% of the Democrats said they weren't going to get vaccinated, compared to 40% of the Republicans. So I'm just going to round these off to 4 decimal places. And let me know if you have a question, where I'm getting those calculations from. So this is the proportion of Democrats in the sample that said no, and this is the proportion of Republicans in the sample that said they weren't going to get vaccinated. So that would be like my starting point for the estimate there. And this comes out to minus 0.3023. Okay, and then for that point estimate, then we would add and subtract the margin of error. And that margin of error depends on 2 things, the confidence level and the standard error. And this problem was asking us to set up a 90% confidence interval. And so if I have 0.9 in the middle, then over here is the missing 5%. So altogether, when I want to find this value over here, right, we would put in the 0.95 and the 0 and the 1. Any questions? And so that comes out, if you're checking this in R, this comes out to 1.645. So that's going to be our Z alpha over 2 value for a 90% confidence level. Any questions where I got that from? Okay, and then now this standard error is a bit of a calculation, but it's just a number crunch there. So we could plug in and compute that. Sorry, I'm not gonna kind of go through that whole calculation. We can do it in R. That makes more sense. So I'm gonna open up R. Is there anything you guys want to ask about before I change the screen share? So I'm using the same R file that we were working with last time, called that confidence interval practice. And so we're on this problem over here. So maybe let me do some of this in R. So I'm going to say dem proportion. That's going to be, that was the 40 out of 368. We'll say Republican proportion. That was the 120 out of 292. This Z value we got by doing Q norm. We plug in 0.950 N1. Here we are using 90% confidence level. And now what I didn't calculate was the standard error. So for that, we've got to take the square root of the Democrat proportion times 1 minus the Democrat proportion, all divided by the number of Democrats, which was 368. And then we're going to add to that the Republican proportion times 1 minus the Republican proportion, and divide all of that by the 292 Republicans. So that was that standard error formula that was on the PDF. And then once we've got all of that, we could just do lower cutoff is going to be the Democrat proportion minus the Republican proportion minus Z star times the margin of error, or excuse me, times the standard error. And for the upper, we add the margin of error. Any questions about the code I'm entering here? And so running this, I don't think there's anything else we need prior to this. I see what I did wrong here. This is good. I have some to make these errors. So R is very, very literal. And it doesn't know that when you put two things next to each other, that means multiply. You actually need to hit the multiply thing there. I forgot one of them. This should work. So these are the cutoffs that I was getting on this one. You guys getting something similar?
Yeah, mine is negative 0.304, and then the upper is negative 300.
So we should be this is one that we should be getting the same answers here, since we all have the same sample. So we shouldn't be getting something different. So maybe did I make a mistake? Are you guys getting?
I got the same.
Yeah, I just caught up when I got what you got.
Okay.
Okay.
Yeah.
So I'll double check mine.
Yeah, my guess is yeah, I mean probably the trickiest part is the standard error formula. Like I forgot a multiply sign here. Just make sure you've got parentheses in the right spot there. Okay, so yeah, so this tells us our cutoffs for this interval.
Yeah, it was a parentheses. I got it now.
Good. Okay. So from this, we could say, there's a 90% chance the interval from lower to upper contains the actual difference in the proportion of all Democrats and all Republicans that do not plan to get vaccinated. This is regarding the COVID-19 vaccine. And since these numbers, they were both negative, right? That gave us good information that it's not plausible to believe there is no difference, right? This interval contained only negative values. So since 0 is not in there, that means there should be some difference, that there is a difference in the proportion of Republicans and Democrats that are not planning to get vaccinated. We saw a difference in our proportions, but it's not clear whether that difference is based on just sampling or whether it's more significant than that. And we had like 10%, 11% of the Democrats said no, about 40% of the Republicans said no. That's a pretty big difference in proportion. So it's not that surprising that we're seeing that difference does seem like it's statistically significant. The very last thing is we could do a score interval. This has a built-in similar to how we had for 1. So that would be prop test, except now since we have 2 different groups, the first thing I do is I enter how many successes were there in each separate group. And again, success here means not planning to get vaccinated. And for the Democrats, right, we had 40 people that said they weren't going to get vaccinated. And for the Republicans, it was 120. So the ordering here matters, and right, I'm not entering all of the Democrat information. First, I'm entering how many successes were there in group 1, how many successes were there in group 2. Then we enter how many observations were there in group 1. So that's the 368. And then there were the 292 Republicans. So this is telling me 40 out of 368, these are Democrats, and 120 out of 292, these were the Republicans. But then we enter the confidence level again, which is 90% here. And then this tells R that I want the cutoffs for the confidence level. And so comparing these, okay, again, they're different because R does the score confidence interval. That formula was the vault confidence interval. So that's why they're not getting the exact same answer, but we can see they're pretty close. Yeah.
It's saying that it couldn't find the function. Is there a specific library that we need to load first?
Nope. No, this comes straight out of the box. So did you put a dot between the prop and the test?
Yeah, typo. Thank you.
Yeah. Yeah, you shouldn't need any packages for these yet. Yeah, okay. Anything else about this one?
So when we calculate the score interval, like by hand using the formula, should it come out to the same thing that it comes out to when you use the prop test?
It should come out close to it. Probably there's some rounding going on that you won't get the exact same thing.
Okay.
Yeah, and so, yeah, since a couple of people are asking about this, just to backtrack, when we were just not treating the sample any differently for Democrats and Republicans or independents, when we just took all of the people and we're just trying to get an estimate for the single proportion, right, here was kind of the Agresti-Cole method. And then here was how we did the score confidence interval. And up here, I didn't use this formula, but here is that formula that was on that worksheet for the lower estimate. And to get the upper estimate, I just changed that minus sign to a positive sign. Otherwise, it's totally the same. And we're going to need to run some stuff up here. But I'm just going to compare. I'm going to do what you did, Stephanie, and just compare what I get when I do these different methods. I might need some of this stuff, so I'm just going to run it all. And this was last time. Yeah, anyway, I think this is what I needed over here. Yeah, so this was calculated from the sample. I think all this stuff was found early. So if I were to run these formulas, oh, I set this equal to false. I wanted to evaluate it now. Oh, and then I want to see the output. So running these formulas in R by hand, I got this, and using the score confidence interval, it tells me that. And you can see mine aren't perfect. This is 2.634. This is 2.637. Okay, so I'm like out to like 3 decimal places. And I think the reason why I'm not getting exactly what R is getting from this is just due to some rounding in here. I entered 29% for p hat, but actually p hat is 413 over 1082, which is not exactly 29%. So I think that's why there's some difference. Okay, any other questions? Okay, then that is it for confidence intervals, and we'll be working on the next worksheet will be a PDF. So I'm not planning to use R for the next worksheet, other than maybe just some calculations. So I'm gonna open up the next worksheet that's up in Canvas. Which for now is going to kind of just be revisiting some ideas from hypothesis tests. I'm taking a look at them from a different way of calculating them. So this is worksheet 16. You guys need me to upload this, or everyone able to track that down?
I have it.
Okay, awesome. Okay, so yeah, just to kind of backtrack about hypothesis tests in general. These were the ingredients that we talked about last time. So, right, we state our hypotheses. You guys did some reviewing about that. And we want to just be sure we're not changing the way we're stating the hypotheses. So we want to be sure we state them correctly using the right notation. Then we're going to find a test statistic. And test statistic is going to measure, so this is slightly new here. We've been thinking about what a test statistic might be, but here we're going to think about the test statistic as measuring, how many standard errors the observed statistic is from the null claim. And then once we calculate that test statistic, we find the p-value. We're going to be thinking about the p-value the same way as we did that before. And then we're going to make a formal conclusion. And this we didn't get, this is kind of new as well. We didn't really get into what do we do with the p-value once we calculate it. We thought about how do we interpret it. And so to make a formal decision when we're doing a hypothesis test, we compare our p-value to the significance level. And so this p-value is calculated based on your sample. Okay, this significance level is chosen at first. It shouldn't be chosen after you calculate your p-value. And in many situations, that's chosen by a regulatory body. If you're trying to develop a new experimental treatment for COVID in the US, you can't set your own significance level. The FDA says the significance level is 1%. So sometimes these are kind of governed, and sometimes as a researcher, you might have a reason for setting different significance levels. That significance level we denote with the Greek letter alpha. And if our p-value is below or equal to or below that threshold, then that's great. That's when we would say our test is significant, when our p-value is less than or equal to the significance level. If the p-value is above that, then we say our test is not significant. And when our test is significant, that means we found that the p-value is so small that the sample is so unlikely to occur if the null hypothesis is true that when the p-value is so small, that gives us good evidence that the null hypothesis is wrong. So we reject the null hypothesis, and it means we have evidence in favor of the alternative. So when a test is significant, the idea is we find the p-value is less than or equal to the significance level, and then we can reject the null hypothesis. And therefore accept the alternative. And when the p-value is bigger than alpha, we don't say that the null hypothesis is true. We say the test is inconclusive. In other words, we don't reject the null hypothesis. I want to make sure my subscripts are clear there. And so the thing that we're going to kind of focus on is what is the final conclusion that we can make, and how do we figure out the test statistic, and from that test statistic calculate a p-value. We were using simulations before, and now we're going to do these more direct calculations. Any questions? Okay, so first example I want to think about is Paul the octopus. So Paul the octopus, Paul is no longer alive, unfortunately. Paul died a few years ago, but he was an octopus in Germany when Germany was hosting the World Cup, and they would put food in these little bins. So this was like Germany was playing Spain. They put food in these two containers, and then they see which container did the octopus go to. That's who he predicted to win. I think that Spain won that World Cup, actually, if I remember correctly. I can't remember. And Paul predicted, so he predicted after the elimination round, there were 8 matches, and he predicted all of them correctly. So he got 8 out of 8 correct. So the question was, right, is Paul some psychic oracle of, football ability, or is Paul just like randomly picking food out of a bin and doesn't care what flag is on the bin? So here the idea is we want to test to see, is there evidence that Paul has psychic ability? Right, and so again, the null hypothesis is always going to be that he doesn't. The boring claim. The alternative here is that Paul does. And once, like Paul started getting these, then other countries started getting in on the action. And I don't want Manny, the Singaporean parakeet, to feel neglected here. He did quite good, but Manny got 6 out of 6 in a row right, and then messed up in the semifinals. So Paul got them all right. And if we just try and test these claims, really hard to put any sort of framework on these statements, right, to test them. So what we're thinking about here would be like what proportion of matches would Paul get? Like what would be the probability that Paul would guess correctly So let's say, overall, each time Paul guesses, he has a probability of P of getting the right winner. So if Paul does not have psychic powers, what are the odds that he's going to pick the right winner?
50-50?
Yeah, you got 2 bins, this one, and this one. He's got to eat something. Either he's going to luckily choose the one of the winning team, or he might just choose the one of the losing team. But that's just saying, right, there's nothing more than randomness going on. So regardless of whether or not, if Paul didn't have psychic abilities, he would have a 50-50 chance of getting it right. And if Paul does have psychic abilities, right, then we would expect that he would have a more than 50% chance of getting them right. And then this example, we've already talked about how we can solve this. We don't need to do any simulations on this. We can set up a null distribution. And so we had 8 matches here. So we repeated this trial 8 times. And so for the null distribution, we set this up assuming the null hypothesis, HO, is true. Okay, that P is 1/2. in which case the null distribution would then be a binomial distribution. We have 8 repeated trials, all independent from each other. Each game, Paul has a 50-50 chance of getting it right. So this would be the scenario if we're flipping a coin, right? Which is the assumption under the null hypothesis. So the p-value here would be the probability of getting a sample as or more extreme than Paul. And Paul got 8 things correct. So we want to know what's the probability that you would get 8 or more correct out of 8, right? So we do include 8 in that, and that's the most extreme that you could possibly get. So this would mean it would be 1/2 to the 8th power. Or we could use binomial distribution to calculate that. So that comes out to a p-value of 0.0039. So essentially what we found is if we looked at the distribution, right, the p-value would just be the area in that last bin. And so if we're using a 5% significance level, and we've got a p-value of 0.0039, then what would be the conclusion here? Just kind of curious, based on this p-value, would we, which of these possibilities would be the conclusion of this test if we're using a 5% significance level? Okay, if you haven't got your answer in, please take another second to get that in. All right, so here are the results. We got 4 votes for reject the null, 1 vote for a fail to reject. And the idea here is we've got the p-value from above. The significance level was 5%. And yes, because our p-value is less than or equal to it, this is great. That's what we want to see. We want p-values small. So this means we can reject the null hypothesis. And we have evidence.
I was going to say I was the one person who chose the wrong one, and I totally, in my brain, was thinking the other one. So if that helps.
That's fine. It's okay. Yeah, so as long as it's clear, I don't mind mistakes at all, but as long as it makes sense why it was the other option, that's the most important thing. And so here, when we're stating our conclusion, I want you guys, this will be on your next homework assignment, not on this one, but I want you to like explain what that means in the context of the problem. So rather than just say, we accept the alternative, it's nice to actually explain what the alternative is. So we have evidence that Paul is a psychic octopus. So according to this test, we actually did statistically prove that Paul is psychic. But sometimes amazing things happen by chance. And that's my guess is that that's what happened with Paul. Maybe I don't know. My significance level would be more than 5%. I think I would have a higher threshold than that. But according to this test, at that significance level, we could claim that there is something beyond just guessing going on.
Out of curiosity, what would be the significance level that you would assign?
I don't know. I guess I don't know too many octopi or what their psychic ability are. I don't know. I guess like the level of my skepticism would therefore set the bar higher. I would be quite skeptical of a psychic octopus, but I guess I shouldn't rule it out. So maybe I would, even if you pick the 1% significance level here, this would pass that threshold as well. So yeah, I don't know. All hail Paul, I guess. He was ahead of his time. At least he used his psychic powers for useful things like predicting World Cup and not for like, saving the planet and things like this. Okay. Let's, yeah, okay. So any questions about that? I think we have done things like that before. It's been a while, but we did like flipping a coin or rolling a die, and the math is pretty much the same. When we were doing tests on means, this is when we tended to use the permutation test. So I want to kind of talk about how this is going to affect how we can calculate p-values when we're doing tests on means. So here, the idea is SAT math scores are normally distributed, and we do have access to like everybody who takes the SAT. We know how they did. So from a couple of years ago, the mean math score was 570, and the standard deviation, that's a footnote, was not 107 to the 15th power. That's really bad to put a footnote on that, was 107. So so these are population values. So we've got the mean and the standard deviation. But what we don't know is, for individual schools, whether they're over or underperforming compared to the national average. So some school, let's say the hypothetical here is they take a random sample of their students and they find that their SAT score, since maybe the students don't have to report it to the high school, so they sample some students, they calculate the average of those students, and now they want to see how are we doing compared to the average? Are we doing about average? Are we doing above or below? So here, our population is not the US, would be kind of all students at this high school. That took the SAT for math. So kind of the boring claim in this scenario would be that this high school is on average with the rest of the performing high schools in the US. In which case their mean would be equal to 570. the alternative would be that they perform better than the average here, because here they are suspecting that they're better, right? So that's why we're going to test in that direction. So this means we want to see whether their mean is 570. Okay, but again, we don't have all of this data from all of the students. We just have data from 25 of their students. Any questions about the hypotheses here?
They look a little different than normal, because we would normally have a difference on the right equals 0.
That's
for
right.
the null hypothesis.
Yeah, so when we do a test on like a single mean or a single proportion, like we did with this one, we're not comparing two different things. So in those cases, when we're doing a test with one population, then we're going to be testing whether that parameter equals a fixed number that might not be 0. So in this case, it's a little bit confusing because you might think we're comparing two populations, but we really just want to think about this high school as the population we're considering, and we want to know what is the mean math SAT score of all of the students at that high school. Yeah, so the claim is, are they average? Average is 570, or are they better? Yeah, you're right. It is a little bit different. That it should feel a little bit different. Yeah.
Thank you.
So here we're going to let X bar denote the sampling distribution for the mean when we pick samples of 25 students. And we're going to set up a null distribution again. So we're going to assume that HO is true. Which is 570. And we also know that the population standard deviation is 107. So from that information, we actually can set up, like we did with the binomial distribution, we can use the central limit theorem to construct a null distribution. Which is going to describe the distribution of sample means. Sorry, this did not update. I think my screen share froze. Here we go. Okay, so we're going to use central limit theorem to get that null distribution. And by the central limit theorem, right, we know that it's going to be centered at the population mean. And what's really important here is that this is the claim in the null hypothesis. So we assume the null hypothesis is true. We're not going to center our distribution at the 613. That's our sample that we observed. And the standard error we get by taking the standard deviation of the population and dividing by the square root of the sample size. So for us, this gives us 570, and simplifying the standard error, we get 21.5. And so now our test statistic is going to be the z-score of our sample mean. Okay, and the z-score is going to be relative not to the distribution of the population, but it's going to be relative to the sampling distribution out of all of the distribution of sample means. So we're going to call this z. So let me just write this down below, actually. So the z-score, the general form here, because it might vary depending on whether we have a mean or a proportion, is equal to like the observed sample statistic minus the claim in the null, all divided by the standard error. We have our sample that was over here. We have the null claim that was in yellow, and then the standard error we just found over here. So for us, that test statistic would be, we found the sample mean of 613. The null claim is that it should be 570. And then the question is, how many standard errors away is it? That's giving us a way of gauging how extreme is this sample. So this comes out to 2.009. I'll cut it off there. So that's the answer to the previous part, I should say. So that's our test statistic. All right, so this is telling me our observed sample was a little bit more than 2 standard errors from the claim in the null hypothesis. So that's how we can interpret that. So basically, what we found is that our observed stat was about 2 standard errors away from the mean, which we would have expected to be about 570. And when we calculate this test statistic, we're just standardizing this so that instead of talking about SAT scores, we're describing how far this is in terms of standard errors. And since we have a one-tail test here, our p-value is just going to be the area in the right tail that I shaded in blue there. So one way we can think about it would be like the p-value would be how likely are we to get a sample that has a mean bigger than or equal to 613? And what we just saw is because the sampling distribution is normal, that's equivalent to saying what is the probability of you having a z-score that is bigger than or equal to 2.009. So I can use R to calculate that by saying 1 minus p norm 2.00901, because we use the 0 and the 1 here because we've standardized the normal distribution when we found the z-score. And so with some rounding, this is what I am getting approximately for the p-value. So that's telling us that that little blue slice of area there is about, 0.0225. I think I missed the 2 here. So that is a change there from how we were calculating p-values, right? So we're not using permutation distribution here, but setting it up in theory, what would the distribution of sample means look like? Here was my sample mean. How does that fit in with the theory? Any questions? So what would be the conclusion of this one here? If we are using a 1% significance level. Okay, take another 10 seconds, please, to get your answer in. I think we got one more person. All right, so in this case, because we're using a 1% significance level, so that would be like the 0.01, and our p-value was bigger than that, right? When our p-value is bigger than the significance level, that's bad. So this actually would be inconclusive. Okay, we would fail to reject the null hypothesis. Any questions? So this stuff over here, I think to me, this was the most important stuff to really focus on. That is how we calculated the test statistic and how we interpret what it means. And then how we use that to find the p-value. These are some new ingredients to hypothesis testing that we didn't necessarily get into before. Okay, so let's do one last example today, and then it's spring break. Then we've made spring break. So here's a case where, okay, let's say, again, this is just going to be, we're testing one population here. And the population here would be all students at CU Denver. And what we would like to know is, okay, are students at CU Denver getting like the typical amount of sleep, or are they not? So kind of the boring thing would be they're no different. The mean sleep for CU Denver students is 8 hours a night. That would be awesome, wouldn't it? And then the alternative here, they're not saying that CU Denver claiming that they sleep more or less than the average. They're just saying CU Denver students differ from the average. In which case, mu would not be 8. Any questions about the setup so far? And so let's see. So what we're told is, right, so this is the population. And so we have a sample of n equals 22 students. And in that sample, their mean was 7.5. So you would collect all this data probably after you set up your hypotheses and you choose your significance level. And this 1.7, this is the standard deviation of the sample. And here's a situation where my population, CU Denver students, I don't know what the variance or the standard deviation for sleep is for CU Denver students, but I do know what the standard deviation for the sample is. So again, we're going to look at the distribution of sample means. Which is going to look something like this, except when we don't know what sigma is, okay, instead, we're going to use a t-distribution with n-1 degrees of freedom. But let's approximate this normal distribution. Our claim is that mu is equal to 8. So this is like the null claim. And we don't know what sigma is, but in its place, we're going to use what we know, which is the standard deviation of the sample. So this normal distribution, the sampling distribution, should be centered at 8. And the standard deviation, or the standard error, excuse me, the 1.7 over the square root of 22, that comes out to 0.3624. And so the test statistic, let me use this down here in a second. Okay, he's going to tell us how many standard errors our observed sample is from the null claim. So it's the same sort of formula that we had before. Our observed sample had 7.5 hours. We claimed that it should be 8 hours. So that's a difference in half an hour. And the question is, well, how many standard errors is half an hour? And so that's why we divide by the 0.3624. Sorry, that comes out to, yeah, I think I had that right, minus 1.3797. So that would be our test statistic. And again, interpreting this in practical terms, I'll say it and not write it. But if we wanted to interpret this in practical terms, we would say that our observed sample of 7.5 hours of sleep is 1.3797 standard errors below the claim that it should be 8 hours. And now the p-value is going to calculate how extreme that is. And since we used S in place of sigma, we're going to use a t-distribution with n-1 degrees of freedom to compute the p-value. Instead of the normal distribution. So rather than say that z is equal to minus 1.3797, this is a t statistic. And now I'm trying to see what is the probability of getting something as or more extreme than the observed. So our degrees of freedom here, right, are going to be 21. And since we have a two-tail test now, our p-value is going to be the sum of the areas in the left and the right tail that are more extreme than our sample. So I could calculate the area in the left tail and then multiply it by 2 to incorporate the extreme stuff on the other spectrum. So if I were doing this in R, the function that we want to use is the PT function, which is like the cumulative probability function for a t distribution. So like we do p norm, except now we do pt, same idea. And with this, there are two inputs. First is what is the t-value, and then the next is the degrees of freedom. We don't enter a mean and a standard deviation, we enter how many degrees of freedom. And then you can check this. I plug this into R, and I got a p-value of 0.1822. And so if we were to do a significance level of 5%, this p-value is quite large by pretty much any metric. So here, our p-value is bigger than the 5% significance level, so the test is inconclusive. So the kind of takeaway, the main point for today is we were doing hypothesis tests for a single statistic or a single parameter. We did one example where there was one population, Paul guessing, and we were doing a hypothesis test on a single mean, on a single proportion. We just did a couple of examples where we were doing a test on a single mean. And so when we're testing means, we typically don't know the population standard deviation. So we're typically doing it more like the way we did it in this problem with a t-distribution. And when we're doing a test on a single proportion, that is when we use binomial distribution. And what we'll talk about after the break is what happens when we compare differences of two different groups and things like that. Okay, so the hypothesis testing, this stuff that we were talking about is not on this homework assignment, but I'll put up a homework assignment over the break just in case you are bored and you want to keep yourself busy over the break. That's always a good plan to start practicing some of the hypothesis tests. But otherwise, your homework for confidence intervals is due tomorrow night. If you have questions, I have office hours tomorrow from 10:30 to 11:30. I'm happy to help you with that. Otherwise, enjoy the break. Sorry that it came so late this semester, but we'll take it. So enjoy the break. And if you have any questions over the break, feel free to reach out with your questions. And otherwise, I'll catch up with you guys in about a week and a half.